This is problem 14 of the QHack 2023 Quantum Coding Challenges, and this one is entitled Ctrl-Z. And what we're being asked to do in this problem is, given a multi-control Z gate with 2 control qubits, what are the circuits that we need to introduce before and after this Z gate so that when we perform a measurement on this first qubit, we get an output that is equivalent to performing the AND operation between qubit J and K. So to solve this problem, the first thing we need to realize is that when using quantum states, a Toffoli gate performs the equivalent of an AND gate. So if we see the truth table for an AND gate, we see that for every combinations of J and K, we always get 0. But only when J and K are equal to 1, we get state 1. And that's what a Toffoli gate does, right? It only flips the input bit, in this case is just 0, when J is equal to 1 and K is equal to 1. So in all other cases, this X gate is not going to do anything and we're going to get 0 at the output. But when J and K are equal to 1, 0 is turned into 1 and we get 1. So that performs an AND operation. So the second thing we need in this problem is to realize that a Ctrl-Z gate, a multi-control Z gate, inverts the phase of only the 1-1-1 state, right? And this is because if we draw it this way, well, if we have 1-1 here, that means that this will apply the Z gate to this last qubit, and the only way we get a phase inversion here is if this qubit is equal to 1. So really, there's no difference in between what we call the control qubits and the target qubits here. That is why sometimes this gate is drawn just as all 3 control qubits. So in other words, we could basically just say that all these 3 are equivalent, or even, if we had that Z gate here in the middle, that Z block in the middle, that would also be equivalent to what we're drawing here. So it doesn't matter where we place that Z block. All we need to realize is that this gate applies a phase inversion when all 3 qubits are equal to 1. Lastly, the identity we need now is something you've probably seen before, is that if we sandwich a Z gate in between 2 Hallamar gates, that's equivalent to having an X gate. So knowing these 3 things, right? So a Toffoli gate performing an AND operation, the fact that it doesn't matter where we place the Z block, it always inverts the phase of the 1-1 state, and the fact that sandwiching a Z gate between Hallamars turns this into an X gate, basically tells us that what we need in between the Ctrl-Z gate is Hallamar gates on the qubit where we want that X gate to show up. So that way, this will give us an AND gate for states J and K. So let's go ahead and code this in PennyLane. So as always, the first thing we're going to do is import PennyLane and NumPy. Then we're going to define our device, which is going to have 3 wires, and then our Q node, which we're going to call AND, and it's going to take as an input states J and K. And here, this is given to us as part of the problem. We just have some conditionals so that if J is equal to 1, it applies a poly gate on wire 1, and if K is equal to 1, it applies a poly X gate on wire 2 to make sure we're applying the correct input to our circuit. And then all we need to do here is just apply a Hallamar gate to qubit 0. Then our Ctrl-Z gate, we can use this QML control, specify the gate we want to control, so a poly Z. Then the control wires, so in this case the controls are 0 and 1, and then the target wire, in this case 2, and then another Hallamar gate. And in this problem, we're asked to just measure the probabilities of qubit 0. So we return QML props of wires 0, right? So now let's go ahead and draw our circuit for, let's say, 1-1. And let's also look at our output. So instead of drawing, just printing the output of this. And here I need to pass the parameter wires to what this QML control returns. So this should be out here. There we go. So we have Halamar, multicontrol Z gate, Halamar, and then the inputs at 1. And this gives us probability of 0 of measuring 0 and probability of 1 of measuring 1. And then we should get 1, 0 for all other options. So here we have it.